I'm going to show you a couple example problems of how to use the empirical rule to find probabilities and percentages. So here we're going to look at the example of IQ tests. And we've remember it follows an approximately normal distribution. Even though it's symmetric, or excuse me, even though it's discrete, we're going to use an approximately normal distribution to estimate the probabilities and percentages. It has a population mean of 100 and a standard deviation of 15. Right? So I always like to kind of write down the mean and standard deviation when doing things like this. I also like to visualize the problems out because that's going to help us as we get into more complex things, even things we're doing right now. It's going to help us make sense of our answer. So for instance, what we're trying to do in this problem is find the probability that a person at random scores below a 70. So how likely is it if we pick somebody out of a hat that they're going to score 70? So what I'm going to do is I'm going to shade that area that we're looking for. We're looking for this likelihood right here, all this red stuff. And what we know is the value of 70 is 2 standard deviations away, 2 standard deviations below. And if we remember, within 2 standard deviations is 95% of your observations. Now, there's 100% in total, right? So if we know that there's 100% in total, someone has to score something. That means we're left with 5%. But that 5% is included in this half of the graph and this half of the graph. We only want this half. So what we need to do is say, hey, our distribution is symmetric. Let's take that 5%. We'll divide it by 2, and we'll end up with 2.5%. So this is that area that we're looking for. And this is how we can use the empirical rule to find this out. If we were to write this with notation, what we would do is we would write this as the probability that a person at random, an X, was greater than 70. And again, we found that area to equal 2.5%. And that's what it would look like in notation. The next problem, we're going to do something very similar, but I want to kind of point out an important difference between this problem and the previous one. Here, we're trying to find the probability that a person at random scores less than or equal to 70. So if I was to write this out notationally, the probability that some random person, some observation, was less than or equal to 70. The only difference between problem 1 and 2 is we're including the value 70. If I was to shade what we're looking for, we would shade all of this area here. Right? And just like before, we know within 2 standard deviations, we have 95% of our data. Therefore, what's left over is going to end up being 5%. And just like before, that's both half of our graphs. You know, they're going to divide that 5% by 2 because they're equal halves, and we end up with 2.5%. Well, wait a second. We just did this out. When we included 70, we're ending up with the same exact area. When we didn't include 70, we ended up with the same exact area, 2.5%. That's weird to think about because some people score 70. We didn't look for 70 previously, and now we are looking for 70. It turns out that what we're doing is using a normal distribution to approximate these probabilities and percentages. And our normal distribution technically goes from negative infinity all the way up to positive infinity. So there are an infinite amount of possibilities in our data set, in our distribution. Even though there's not an infinite amount of IQ scores, we're using this infinite distribution to estimate these things. And what we're trying to find is the likelihood of obtaining one specific outcome. Specifically, the value of exactly 70. How likely is it that we get exactly 70? Well, that's one outcome out of an infinite amount of possibilities. This comes out to equal 0%. So there's essentially a 0% chance that we end up with getting one specific exact outcome. And because of this, because we're using a continuous distribution, the normal distribution, to approximate a discrete distribution, we can end up with a situation like this, where intuitively the probability should go up. Now that we're including people who score an IQ of 70, that probability should be higher. Previously we weren't, now we are. But based on how we're solving these probabilities and percentages using this normal distribution, the likelihood of one specific outcome is 0, so it's actually not going to affect or change our probabilities at all. What we were actually doing in problem 1 is we were looking for values less than 70. So technically, because we're using a continuous distribution, we were including values here like 69.9999999, 69.9999998. We were including all of these different values even though you couldn't obtain it. So whether we included 70 or not, we are essentially finding the probability of getting a 70 or less, because the likelihood of getting exactly a 70 is 0. So that's something important to keep in mind when we go about these things, and something to make note of. The last problem we'll go over is a greater than problem. So here we're trying to find the probability that a person at random scores greater than an 85. So again, I like to shade the area just to get me a sense of, well, what area are we looking for? And we are looking for all of this stuff right here, all of this area. And all this good stuff right here. And so if we look at 85, maybe write the mean and standard deviation here. 85 is one standard deviation away. And we know within one standard deviation, we know is 68% of observations. Well, what's left? Because what we just found is this inside area. Right? We just found this inside stuff. We still have this area to figure out. Well, just like we did before, we know that there is a 100% chance we get some value. There's 68% within one standard deviation. We'll end up with 32%. But that 32% is looking at both halves of this graph, this stuff over here and this stuff over there. Well, we only want just one side of that. We just want this stuff. So let's take that 32%. We'll divide it by 2, and we end up with 16%. So we'll add these two areas together. That inside 68% plus that half of that outside area of 16%. And we end up with 84%, or a probability of 0.84. If you want to write it as a percent, or if you want to write it as a probability, either is okay with me. But what this is saying is there's an 84% chance a person at random will score an 85 or above. And if we wanted to write this out notationally, we would write the probability that X is greater than 85.